So this part, we're going to talk about discrete distributions. So there are quite a few discrete distributions that are common enough that they have names and formulas. Okay? And everything that we learned how to do before still applies. This is just, we use it so much that they came up with the formulas for it to make it simpler. The first one is actually a pretty boring one. It's called Bernoulli random variable. And we're just kind of learning as a preliminary step. So the Bernoulli random variable can only take two values. So kind of like yes or no, heads or tails, success or failure. Okay. We could use it to do things like model one coin toss, so heads or tails, whether a valve is open or shut, whether an item is defective or not. And this is the key thing here to make it Bernoulli, is we do it when we only have one trial, or we only do the experiment once. But this is why it's kind of boring, because you don't usually toss a coin just once or roll a die just once. You usually want to do things multiple times. But for now, let's see what happens if you do it just once. There are two possible x values, which we'll call 0 and 1. Okay? Because if you think about, like, if you're tossing a coin, it's heads or tails. Depending on if you're interested in heads, you only have either 0 heads or 1 heads as options. So you have 0, 1. And the probability, the 1 is always the thing that you're interested in. So the 1 is our thing of interest. Okay, and so you have a p probability to get what you're interested in. So a p probability that you get 1 head, or a p probability that the valve is, say, open, just depending on what you're actually interested in. And then your other one, outcome, is going to be the 0. And 1 minus p would be its probability, because all probability has to add up to 1. The probability that the item occurs, the thing that you're interested in, is p, and we're going to call p a parameter. So we haven't talked about the word parameter, but parameter is just some kind of number that defines our distribution. So in this case, p, whatever your probability is, defines this entire distribution, and that's why it's called a parameter. Our probability p can be between, well, what two numbers do you think it would be in between? It's a probability, so all probabilities are always between 0 or 1. And let's make a note for ourselves that parameter is a value that defines a distribution. Okay. And as far as we're taking notes, the Bernoulli random variable can only take two values, which is always 0 or 1. Those are the only two things a Bernoulli random variable can do. So in our first example, which really isn't an example, it's kind of a proof, we'll let x be a Bernoulli random variable, and we'll find the expected value and variance. So this is why this section is kind of nice, because we get to review everything that we learned in previous sections. Okay. Let's first write down, how do we find expected value for a random variable, for a discrete random variable anyways. This is starting from the basics, just from our PMF. Expected value of x is the sum of each xi value times the probability. And we'll also write down the variance of x. There's different ways you can do this. Okay. You can do the sum of each xi value minus the mean squared times the probability. But that one's actually pretty hard to compute. You'll get the same answer, but it's harder. Okay. It's easier if you do this one. So you'll do the variance of x equals the expected value of x squared minus the expected value of x squared. And I actually did it both ways earlier today, just to kind of see, was it harder? And the second way is just much easier algebraically. And you might wonder, for a discrete random variable, how would you find the expected value of x squared? We'll come back up. Expected value of x was the sum of x times pi. So what do you think it'll be for x squared? You'll just do x squared, each x value squared, times its probability. So just like when we were doing it for the continuous random variables, if you have x, you just do the sum of x times p. If you have x squared, you do the sum of x squared times p. So our discrete and continuous are fairly similar. It's just that continuous is so much easier to do algebraically, because you just get to use calculus instead of doing sums. Let's see. Okay, so x is Bernoulli. Find the expected value of x. Okay, so we just take the sum of each xi value times its probability. So our first x value is 0, and its probability is 1 minus p. Our next x value is a 1, and its probability is p. This is simple enough algebraically, because the 0 cancels this entire term, so we just get p. That's our expected value. Now, as a preparatory step to find our variance, let's find the expected value of x squared. So this one is just the sum of each xi value squared times the probability. So my first x value is 0, and you'll square it, and then you'll do 1 minus p as its probability. Plus my next x value, which is 1 squared times its probability. And it turns out, interestingly enough, we still get p for the expected value of x squared. That's just a coincidence. Okay, now let's find the variance of x. So it's the expected value of x squared minus the expected value of x squared. So expected value of x squared, in our case, was p. And now the expected value of x was also p, but we have to square that one. So we just have p minus p squared, or usually we write it as p times 1 minus p. Don't ask me why, that's just kind of tradition. So we have the expected value for Bernoulli and the variance for the Bernoulli. So all of these formulas that we learned in this chapter, they didn't just come from nowhere. They came from people writing it out, doing everything step by step. And it just turns out that these have simple enough formulas that we can find formulas for expected value and variance that always work. So let's look at this example. Let's say we want to toss a biased coin once. Now that once means it's going to be the Bernoulli. Okay, once, and the fact that x is the number of heads, so we just care about heads or not heads. I know from past experience that the probability of heads is 0.4. Okay. Let's find the expected value and variance. So one of the first things you want to do is write down the information they tell you. So like x, which is the number of heads, is going to be distributed Bernoulli. Now you haven't actually seen that little symbol yet, have you? This little symbol right here means distributed. Or that it belongs to the Bernoulli distribution, or that the Bernoulli distribution is a good way to describe it. And so you'll see that a lot. We'll keep using that for different things. That means distributed. So it's the Bernoulli, and then you would have to tell me that p equals 0.4. So probability of heads is 0.4. So the expected value of x for a Bernoulli is just always equal to p, which in our case is 0.4. So super easy to find that expected value. And the variance of x is equal to p times 1 minus p. So in our case, it'll be 0.4 times, let's see, 1 minus 0.4 is 0.6, so we get 0.24. So there's our variance and our expected value. So again, what was happening is people were doing these applications, and as they did it, they're like, hey, wait, we're seeing a pattern. We're seeing this pattern come up over and over. Why should we keep finding the expected value and variance every time? Let's just come up with a formula and a name for the distribution. So that's Bernoulli. And the reason we care about Bernoulli is that it actually leads to the binomial distribution, which is more interesting. Because the binomial distribution, you still have either a success or failure. Okay, yes or no, 0 or 1, but you're going to do it n times. So this is like flip a coin 10 times, or do something 10 times or 20 times. So here's what happens, or the requirements to use a binomial distribution. The first is that you have to have a fixed number of observations n. Or in other words, you know in advance how many times you're going to do your experiment. So I would usually abbreviate this as you should have n trials. And your n observations all have to be independent. Independent, again, meaning that they can't affect each other. Okay, and every observation is classified as either a success or failure, or in other words, there's only two possibilities. It's always like heads or tails, open or shut, two possibilities. And the last one is that the probability of a success, P, is the same for each observation. So your probability doesn't change. If you have an application where it fits all of those four criteria, you can use the binomial distribution. And so what you do is you're always interested in counting your successes. So to count your successes, X would be the number of successes you get, and that distribution will be called the binomial distribution. And it actually has two parameters, N and P, because both your number of trials and your probability affect your distribution. We would say that X is distributed, so there's that little distributed, with a B and NP. Sometimes you do a B, sometimes they'll do a BIN, sometimes you can actually write it out binomial NP. It just depends on which textbook you're using, but that all means that it has a binomial distribution. And remember, N is your number of trials, P is your probability. Now, as part of your homework, you're actually going to go through and discover how they came up with this formula. Okay. But for tonight, we'll just look at our formula. So we have this probability mass function. The way you find the probabilities, if you want the probability that X equals some specific value, you'll do N choose X, P to the X, 1 minus P to the N minus X. So what do each of these pieces mean? Why do they have those pieces in the formula? So N choose X, does that look familiar? In section 1.7 we talked about permutations and combinations. What is this N choose X? That is a combination, remember, from section 1.7. On your calculators, if you have a TI calculator, you would do things like look for the NCR button. If you have, say, Casio, you would look for something, well, it's actually an NCR button. It just depends on how you put it in. So usually on your calculator, you'll have something that looks like this somewhere in your menu, so you can do that combination. So we have N choose X equals N factorial over X factorial N minus X factorial. So why do we have that in there? It's because, well, sometimes they call it binomial coefficient just because we use it in the binomial distribution. But it accounts for the number of ways in which we can choose X successes from N observations. So it's N choose X, again, is N factorial over X times N minus X factorial. Now this P to the X accounts for our probability of getting X successes. So P is the probability of success, and we raise it to the X power because you need X successes. And 1 minus P, that's the probability of failure, and you need N minus X failures. So again, for now, we'll just use that formula. As part of your homework, you'll see how we discovered it. But first, before you can use the binomial distribution, you need to know if it's appropriate in your situation. Okay, so we'll practice that first. So for each of the following situations, let's check our conditions to see if the binomial distribution is appropriate. And if so, what would be X, N, and P? Now, just as a note on our exams, I'm not going to tell you this is the binomial distribution. I'm going to give you a story problem, and you have to recognize it as the binomial distribution. Let's see. So each child of a particular pair of parents has a probability 0.25 of having type O blood. Genetics say that the genes one child gets shouldn't affect the genes the other child gets. What's that telling us right there? That they are independent, right? They don't affect each other, so independent. If these parents have 3 children, let's count the number of children with type O blood. Okay. So there's a few things here you want to key into. First of all, you know that they're having 3 children. So we have 3 trials, or N equals 3. We know in advance how many times we're doing something. Okay. They told us that they were independent. or they didn't affect each other. Okay. They told us that we are kind of counting the number of children. We want to count that number of children. That count is kind of a big deal too. That kind of keys you into it might be binomial. It's not the only way we count things, but it keys you into it might be binomial. And then let's see, we're looking at people that have type O blood. So we could say it's either type O or not type O. And so you have either kind of that like yes or no, 1 or 0, only 2 possible options. And finally, did it tell us the probability of having our success or having type O blood? They said we have a 0.25 probability of having type O blood. So our probability is 0.25. So that fits all 4 criteria. We know in advance that there's 3 trials. They were independent. It's a success or failure. It's really only 2 options. And we had our probability of success is 0.25. And so this would be binomial. And n equals 3. And p equals 0.25. Let's see. Now number 2, we have replacement heart valves made of animal tissue have a probability 0.77 of performing well for 15 years. Therefore, the probability of failure for a heart valve would be what? So we know the probability of it doing well is 0.77, so the probability that it fails would be 1 minus 0.77 or 0.23. Okay. So that's just kind of a little preliminary step. Now let's count the number of patients with heart valve failures in a group of 500. Okay. Notice again here that keyword count. Count doesn't mean that it's binomial, but it means that binomial might work for it. Now go ahead and check everything else. Let's see. So first, let's kind of go through on each thing. We could say that they either fail or not. So there's 2 options. Let's see. We know we're looking at 500 people. So n equals 500. We know in advance what we're looking at. Let's see. Probability. They tell us we have a probability of 0.23. They didn't say anything about like it changing, so we'll just say it's 0.23. And let's see, the last thing is, should it be independent or not? Should my heart valve affect your heart valve? Okay. Probably not. I don't see any reason they would, assuming that we're not like talking about they were all by one doctor or something. So we'll just say independent here, so it fits all 4 criteria. So it is binomial. N equals, let's see, 500. P equals 0.23. Oh, and they didn't actually tell us what x is. You should always kind of do that first. What would make sense? We want to count the number of patients with failures. So x is the number with failures. You should always write down what x is going to be. So up here, x was number with type O. And the last one here, we want to draw 2 cards from a standard 52 card deck with replacement. Let's consider drawing a heart a success. And it doesn't actually tell me what I want to count, so let's kind of read into this, do the implications. If the heart is the success, that's what we would want to count, so x would be the number of hearts. Okay, let's see if it would work. Okay. So first, can you say that this would be just 2 options? Technically, you have hearts or diamonds or spades or clubs, but if we only care about the number of hearts, we could define it as hearts or not hearts. And if that's how you define it, then we still have only 2 options. Okay. let's see, do you know how many things you're going to look at? How many times you're going to do something? It says draw 2 cards, so we're only going to do something 2 times. Okay, let's see, we need a probability of hearts since that's what I want to count. And what is the probability of hearts? 0.25 or 1/4. And as far as drawing cards, let's see, notice they said it's with replacement, so I draw out my first card and then I put it back. So does the first card affect the second card? Nope. So again, that is independent. So we have binomial of n equals 2 and p equals 0.25. Now, because I had already published the course reader months ago, I couldn't go through and change this. So the videos kind of skipped through. So we did 3 examples here of whether or not it's binomial. And then you'll notice it's right here. Now I want you to go home and watch this video in a couple days. And it's just more practice, but these are actually some examples of where it's not binomial, so you can see the other side. And so we're going to now skip ahead to page 65, where we'll practice finding some binomial probabilities. So example 93, a gas station receives 5 cartons of milk each week. At this station, 75% of the milk cartons are sold before they expire. Of course, the gas station has to throw away any milk that expires. Makes sense, right? Let's let X be the number of milk cartons they have to throw away next week. So, X equals the number we throw away. And that's important because it started talking about the number that are actually sold, but in the end, what we care about here is the number that are thrown away. Okay, so first, could we use the binomial distribution? Now, one of the key things here when it said let X be the number, anytime I'm trying to count or find a number, it doesn't mean it's going to be binomial, but it means that maybe binomial would work. So it's the first thing that says, okay, go check binomial stuff. Let's see, so one of the first things you check is, do you know in advance how many you're looking at? Well, they tell us they only get 5 cartons of milk each week, so we know that n equals 5. Okay, then can you narrow it down to just 2 options? So in our case, you can either throw it away, or I guess you can sell it, right? Either you sell it or you throw it away at the end of the week. So 2 options. Let's see, should they be independent? 1 carton of milk going sour shouldn't affect the other cartons. Okay, they don't cross-contaminate there. And do you have a probability of a success? Okay, or in this case, we're throwing it away. That's might not seem like a success in the business world, but it's what we're counting. So what's the probability of what we're counting or throwing it away? If 75% are sold, then that means 25% expire and are thrown out. So our probability would be 0.25. So this does look like it would be binomial. And we have n equals 5, p equals 0.25. So yes, you can use the binomial distribution. So now, what is the probability that 2 of the 5 milk cartons expire? So first, let's write down our formula, because I'm sure you haven't memorized it yet. The probability that x equals some specific number will be n choose that specific number times p, the probability of success, times or raised to the power of how many successes you want, times 1 minus p, the probability of failure, to the n minus x, because that's the number of failures that you're looking for. Okay, so now the probability that x equals 2 would be, okay, n is 5, so 5 choose 2. My probability of success is 0.25, and I want to get 2 successes. And then 1 minus 0.25 would be my probability of failure. Okay? And then think about it this way. If you want to throw away 2 milk cartons, how many are actually not thrown away or sold? Okay? There's 5 total. You throw away 2, that means 3 are actually sold or not thrown away. So that's why it's this 5 minus 2, because that's basically what's left. At this point, you need to put it in your calculator, and you get 0.2636. Now, number 3 is, what is the probability that less than 2 of the milk cartons expire? So we're looking for now the probability that x is less than 2. Now, it turns out they were never able to actually come up with a nice CDF formula for the binomial distribution. So you have to do this one by one. So you say, okay, well, if x is less than 2, then that means x equals 0 or x equals 1, right? Those would be my 2 options for things that are less than 2. So I have to find both of these probabilities one at a time. So the probability that x equals 0, okay, you have to use this formula up here. So you'll do 5 choose 0, 0.25 to the power of 0, 1 minus 0.25 to the power of 5. Okay. Or again, this is how many ways out of those 5 milk cartons could I choose 0 that expire. And then I want, the probability of expiring is 0.25, but I want to expire 0 times. And the probability of selling is 1 minus 0.25, and if 0 expired, then that means 5 of them must have sold. So 0.2373. And traditionally, when we're doing these probabilities, for some reason, we always write them out to 4 decimal places. And the probability that x equals 1 would be 5 choose 1, 0.25 to the power of 1, 1 minus 0.25 to the power of 5 minus 1, or 4. So 0.3955. So once you found each of those individual probabilities, and the probability that x is less than 2, is you just add all of those up. So 0.2373 plus 0.3955 equals 0.6328. Now, some calculators have these binomial probabilities built in, which is nice if you have to do more than 1 or 2, because it gets tiring doing it by hand. You also have, well, I haven't checked the back of this book, but most statistics books have a bunch of binomial tables as well, because they realize it takes a long time to do it by hand. Because there wasn't any shortcut. They didn't actually have the CDF formula built in anywhere. So any questions on how we did this problem? But there's one more thing we need to learn. So everything we've done so far, we've always gone and talked about the mean, or mean means expected value, and standard deviation. So let's figure out how we can find the mean and standard deviation. So again, this is kind of our proof, or our generic thing that works all the time for binomial distributions. So if x has a binomial distribution, so for x to be binomial, what you're basically doing is, let's say we're flipping a coin 5 times. The first time I flip a coin, I write down either a 1 or 0 for either heads or not heads. The second time, I write down either a 1 or 0. The next time I write down either 1 or 0, 1 or 0. I do that 5 times, and at the end, I add them all up, right? Because if I got 3 heads, then I would have written down 3 ones. I add them up, and I get 3. Okay, so what it really is x, anytime you're binomial, x is really like x1 plus x2 plus up to xn, where x1, x2, up to xn are Bernoulli random variables. And Bernoulli random variables have a mean, or expected value of xi equals p, and the variance of each one is p times 1 minus p. So again, Bernoulli was just one trial. If you do it lots of times and you add it up, you get to a binomial random variable. So So the expected value for a binomial, or expected value of x, is we have to do the expected value of each one of those added up. So we've been practicing with things like this. What did we do? You just take the expected value of each one, right? So expected value of x1 plus expected value of x2 plus all the way up to expected value of xn. But each of those expected values is always just p. So p plus up to plus p. And how many of those p's did we have? N of them. So we have np. So our expected value is always going to be n times p. And the variance of x, we're going to do the exact same thing here. So we just write it out. It's really the variance of x1 plus x2 plus all the way up to xn. And luckily, because we know that they're independent, they're not affecting each other, we can just do the variance of each one separately and add them up. So variance of x1 plus variance of x2 plus up to the n, which is variance of xn. Now each variance is p times 1 minus p, and the next one is still p times 1 minus p, up to the last one was p times 1 minus p. So we had n of those that we added up, so it's n times p times 1 minus p. So you can see here at the bottom, I've written it out. This is kind of my official formulas for a binomial distribution. The expected value of x is n times p, and the variance of x is n times p times 1 minus p. Okay, so again, we use the binomial distribution enough. We don't want to have to come up with these formulas every single time. We want to have it memorized. But they're not just being pulled out of thin air. It's just all of these rules that you guys learned. Someone just went through and did it in advance and found the generic form. Okay, so if you go and you watch your video, there's this example is in the video. Okay, and I'm going to do example 97 with you here. Okay, so let's say that Nick has a 0.15 probability of bowling a strike on any frame when he goes bowling. A bowling game consists of 10 frames. Let x be the number of strikes he gets in a game. So first of all, would this be binomial? Well, it is in section 3.1, so probably. Okay, but you could say, okay, let's see, he's doing it 10 times. We know he has a 0.15 probability each time. What he gets on one frame shouldn't really affect the next frame. Okay, so they should be independent. And it's either a strike or not. Okay, so that does seem like it would be binomial. Because it's binomial, now number one gets really easy. What is the expected number of strikes per game? The expected value of x is just, what did we say? N times p. So 10 times 0.15 gives me 1.5. So he can expect to make about 1.5 strikes. And what is the standard deviation of the number of strikes per game? We didn't learn a formula for standard deviation, did we? But we learned a formula for variance. Variance is np times 1 minus p. So 10 times 0.15 times 1 minus 0.15. I didn't actually write this one down. So it's 1.275, but that's the variance. They said find the standard deviation. So the standard deviation is just the square root of variance. So the square root of 1.275 is 1.129.